Welcome to the course Biomedical Instrumentation in Sensors. I am Dr. Pankaj Kumar Mishra, currently working as a professor in the Department of Electronics and Telecommunication at Rungta College of Engineering and Technology, Bhilai. Now, the analyzing biomedical signals in the frequency domain is crucial for gaining valuable insights and information that may not be readily apparent in time domain. Here are some key reasons why analyzing biomedical signals in the frequency domain is important, or why Fourier transform is so important. Now, here in this lecture we will deal with Fourier transform. The Fourier transform is so important in biomedical signals. First one is identification of frequency components. Biomedical signals often contain various frequency components, each associated with specific psychological phenomena. Analyzing these signals in the frequency domain allows for the identification and characterization of these components, such as heart rate, respiratory rate, or a specific oscillatory pattern in EEG signals. Second one, noise separation and reduction. Biomedical signals are susceptible to noise and interference. Frequency domain analysis enables the separation of signal components from noise, making it possible to filter out unwanted frequency and enhance the signal to noise ratio, leading to more accurate and reliable data. Third one is quantitative assessment. Frequency domain analysis provides quantitative measures of signal characteristics. For example, in an electrocardiogram ECG signals, the spectral analysis can be quantify the power in different frequency bands, helping in the assessment of heart rate variability in identifying abnormalities. Fourth one, detection of abnormalities. Some medical conditions and abnormalities manifest as a specific change in frequency component of biomedical signals. Analyzing signals in the frequency domain can reveal these deviations, aiding in early detection and diagnosis. For instance, the presence of abnormal spikes or patterns in EEG frequency spectra can indicate neurological disorder. Fifth one, monitoring and feedback. Continuous monitoring of frequency components in biomedical signals is essential for patient care. Clinicians can track changes in frequency parameters over time, enabling them to adjust treatments and intervention as needed. This is particularly important in critical care setting. Sixth one, treatment optimization. In therapies such as deep brain stimulation for Parkinson disease or epilepsy, analyzing signals in the frequency domain can help optimize treatment parameters by targeting specific frequency components associated with the condition. This leads to more effective and personalized treatment approaches. Seventh, research and biomarker discovery. Frequency domain analysis is fundamental in medical research. It allows researchers to explore and discover novel biomarkers associated with various diseases and conditions, paving the way for advancement in diagnosis and treatment. Eighth one, signal compression and transmission. In telemedicine and remote monitoring applications, frequency domain analysis can be used to compress signal data for efficient storage and transmission. This is specifically important when dealing with large volumes of biomedical data. In summary, analyzing biomedical signals in the frequency domain is essential for extracting meaningful information, quantifying signals characteristics, detecting abnormalities, and optimizing treatment approaches. It is a valuable tool for healthcare professionals, researchers, and engineers working in the field of biomedical signal processing, enabling improved patient care and medical advancement. Certainly, Fourier transform is indeed a powerful and indispensable tool in the field of biomedical signal processing. In the realm of biomedical signal processing, we encounter a vast array of complex and intricate data generated by the human body's psychological processes. To make sense of this data and extract valuable insights, we rely on a versatile and indispensable tool, the Fourier transform. It is the key that unlocks the hidden secrets within biomedical signals, enabling us to uncover vital information about the human body's inner workings, diagnose medical conditions, and drive innovations in healthcare. Let us delve deeper into why the Fourier transform holds such a pivotal role in our quest to decode the language of life. Absolutely, the Fourier transform is an exceptionally powerful tool for biomedical signal processing. It serves as the cornerstone of signal analysis in this field, offering several critical advantages and application. Frequency component identification. Frequency component identification. Biomedical signals often contain a mixture of different frequency components. The Fourier transform allows us to identify and isolate these components. For instance, it helps identify heart rate frequencies in ECGs or specific brain waves frequencies in electroencephalogram EEGs. Filtering. Filtering is a crucial aspect of biomedical signal processing, whether it is removing noise from ECG recording or isolating a specific frequency bands of interest in EEG signals. The Fourier transform facilitates the design of appropriate filters in the frequency domain, enabling precise signal enhancement. Third one, power spectral density analysis. Biomedical signals often needed spectral analysis to understand their frequency characteristics. The Fourier transform is instrumental in calculating the power spectral density, providing insights into how signal power is distributed across different frequencies. PSD analyzing is essential for interpreting psychological process. Fourth one, harmonic detection. Some biomedical signals like electromyograms, EMG or phonocardiograms, PCGs exhibits harmonic components. The Fourier transform aids in detecting and quantifying these harmonics, which can reveal information about underlying muscle activity or heart sound. Fifth one is event detection. In application such as EEG analysis, the Fourier transform plays a crucial role in the event detection. It helps identifying specific frequency patterns associated with events like seizures or brain activity changes. Feature extraction. 6.1 biomedical signal processing often involves extracting relevant features for further analysis or disclassification. The Fourier transform can be used to extract frequency based features that are instrumental in tasks like heartbeat classification, sleep stage detection or disease diagnosis. 7th one, visualization. By transforming signals from the time domain to frequency domain, the Fourier transform enables the creation of visual representation like a spectrogram or frequency domain plots. These visualizations aid in the interpretation and analysis of biomedical data. In essence, the Fourier transform acts as a bridge between the time domain where biomedical signals are recorded and the frequency domain where crucial information about the underlying psychological process resides. Its ability to dissect complex signals into their constituent frequencies empowers healthcare professionals, researchers and engineers to make informed decisions, diagnose medical conditions and pioneer advancement in healthcare technology. The Fourier transform and the concept of time domain and frequency domain signals. First one is time domain signal. A time domain signal is the representation of signal in which the horizontal axis represents time and the vertical axis represents the amplitude of the signal at each point in time. In simpler terms, it shows how the signal amplitude varies with time, and its former way we visualize signals in everyday life. For example, if we were to record the sound of a muscle's note, the waveform you see on an oscilloscope or a digital audio editor is a time domain representation. It shows how the air pressure amplitude changes over time as the note is played. Second one, frequency domain signal. A frequency domain signal on the other hand represents a signal in terms of its constituent frequencies instead of time. Horizontal or on the horizontal axis, the frequency domain plot has frequency on the x axis and amplitude of each frequency component on the y axis. This representation provides information about which frequencies are present in signal and how strong they are. A frequency domain signal does not show how the signal evolves over time, but rather what frequency components are making up the signal's overall shape. Fourier transform, third one. The Fourier transform is a mathematical tool used to convert a signal between the time domain and the frequency domain. In simple terms, it takes a time domain signal like an audio waveform and decomposes it into a set of sinusoidal components, each with its own frequency, amplitude and phase. This transformation is extremely valuable because it allows us to understand a signal's frequency composition. It answers questions like what are the fundamental frequencies present in the signal, how much of each frequency is there. In summary, the Fourier transform is a fundamental mathematical tool that allows us to examine a signal's frequency content by converting it from the time domain to the frequency domain. It provides insights into the various sinusoidal components that constitutes the signal, making it a crucial tool in the field ranging from engineering and physics to music and biomedical signal processing. Now come to the discrete Fourier transform and its role in the processing digital signal. Discretizing signals. In real world, signals often occur continuously over time, forming analog signals. These analog signals are represented by infinitely many data points along a continuous time scale. However, in many practical applications, we need to work with a digital system which operate with discrete data points. This process of converting continuous analog signals into discrete digital signals is known as discretization or sampling. Discretization involves taking regular samples of the analog signals at specific time intervals. The result is a sequence of discrete values, often referred to as a time signal. The discrete Fourier transform is a mathematical transformation used to analyze the frequency components of discrete time signal. It provides a way to convert a sequence of n discrete data points into its frequency domain representation. Role of DFT, discrete Fourier transform, in processing digital signals. The DFT plays a central role in processing digital signals for various reasons. First one is frequency analysis. It allows us to analyze the frequency content of a discrete signal. By computing the DFT, we can identify which frequencies are present in the signal and their respective magnitudes and phase. Spectral analysis. DFT is instrumental in calculating the power spectral density of a digital signal. PSD provides insights into how signal power is distributed across different frequency components. Filtering. Frequency domain filtering such as low pass, high pass or band pass filtering is often applied using the DFT. This enables noise removal, signals enhancement or the isolation of a specific frequency band. Feature extraction. DFT is used to extract relevant frequency domain features from the signal which are valuable for various applications including pattern recognition and classification. Compression. In some applications, DFT based techniques are employed to compress signals for efficient storage and transmission while preserving essential frequency information. Inverse DFT. The inverse DFT allows us to reconstruct the original time domain signal from its frequency domain representation, which can be useful for various signal processing tasks. In the digital domain, where signals are inherently discrete, The DFT serves as a fundamental tool for understanding and manipulating signals in both time and frequency domains. It is widely used in areas such as digital signal processing, telecommunication, audio processing, image processing, and many other fields where digital signals are encountered. Fast Fourier transform. Its significance in efficiently computing the discrete Fourier transform, its algorithm aspects, and its notable speed advantage over the DFT. Importance of FFT for efficient computation of DFT. The discrete Fourier transform DFT is a powerful mathematical tool for analyzing the frequency components of a signal in the frequency domain. However, its direct computation can be computationally intensive, especially for large data sets. The fast Fourier transform is an algorithm specifically designed to compute the DFT efficiently. It dramatically reduces the number of arithmetic operations required for the transformation. The FFT is crucial in various applications, including signal processing, telecommunication, image analysis, and specific scientific computing, where rapid frequency analysis is required. Algorithm aspects of FFT. The FFT is based on the divide and conquer strategies, where the DFT of a composite signal is computed by recursively breaking it down into smaller DFTs. The Cooley-2K algorithm, one of the most well-known FFT algorithm, divides the signal into two halves, computes their DFT separately, and then combines them to obtain the DFT of the original signal. This process is repeated recursively, dividing the signal into smaller and smaller segments until the DFTs of the individual segments are computed. The key idea is to exploit the periodicity and symmetry property of sinusoidal function to optimize the computation, reducing the time complexity from n square direct DFT to n log n operations for the FFT, where n is the number of data points. Speed advantage of FFT over DFT. The primary advantage of the FFT over the direct computation of the DFT is its remarkable speed. The FFT algorithm's time complexity of n log n makes it significantly faster than direct DFT computation, which has a time complexity of n square using conventional methods. For large data sets of high resolution signals, the FFT computational efficiency becomes crucial. It allows for real-time processing of signals and data analysis in a fraction of the time required by the DFT. The speed advantage is specifically evident in applications like audio signal processing, image processing, and telecommunication, where rapid Fourier analysis is essential. In summary, the Fourier transform is groundbreaking algorithm that efficiently computes the discrete Fourier transform of signals. It divides and conquer approach, such as the Cooley-2K algorithm, allows for a significant reduction in computational complexity compared to direct DFT computation. This speed advantage makes the FFT a fundamental tool in digital signal processing and various other fields, enabling fast and efficiently frequency analysis of digital data. Analyzing frequency component is essential in biomedical application for several compelling reasons. Psychology and functionality. The human body and other biological system exhibits a wide range of psychological processes that manifest as various signals such as electrical, mechanical, or biomedical. Many of these processes involve periodic or rhythmic activities, and their frequency components contain vital information about the underlying psychological functions. For example, the heart electrical activity in electrocardiogram contains frequency components that reveals the heart rate and rhythm. Analyzing these components helps diagnose arrhythmia Eons and heart diseases, disease detection and diagnosis. Disease and medical conditions often manifest as alterations in normal psychological process. By analyzing the frequency components of biomedical signals, healthcare professionals can identify abnormalities, detect disease, and monitor the progress of treatments. For instance, in sleep medicine, the analysis of EEG frequency components helps diagnose sleep disorders such as sleep apnea or insomnia. Noise reduction. Biomedical signals are frequently contaminated by noise, artifacts, and interference from various sources such as electronic equipment or environmental factors. Analyzing the frequency components allows for the identification and removal of noise, enhancing the quality and accuracy of the signal. This is particularly critical in applications like brain computer interfaces, where precise EEG signals analysis is essential. Psychological phenomena. Biological system exhibits a diverse range of psychological phenomena, some of which have characteristic frequency signatures. Examples include brain waves, frequencies in electroencephalogram (EEG), muscles contraction frequencies in electromyograms (EMG), and respiratory frequencies in respiratory rate monitoring. Analyzing these frequency components and helps researchers and clinicians understand the quantify these phenomena. Treatment monitoring. In the context of medical treatment, monitoring the frequency component of biomedical signal provides valuable feedback on the efficiency of intervention. For example, in cancer therapy, changes in the frequency component of tumor associated signals can indicate treatment response or resistance. 6.1 Customized treatment plans. Analyzing frequency components allows for the customization of treatment plans based on an individual's unique psychological characteristics. In personalized medicine, this information can lead to more targeted and effective therapies, minimizing side effects. Research and discovery. Biomedical research often involves upcoming new insights into the functioning of the human body and the mechanism of disease. Frequency analysis of biological signals can reveal hidden patterns and phenomena, facilitating discoveries in advancement in healthcare and life sciences. In summary, analyzing frequency components in biomedical application is paramount for understanding the underlying psychological processes, diagnosing disease, monitoring treatments, and advancing medical knowledge. By extracting and interpreting the frequency content of biomedical signals, researchers and healthcare professionals gain crucial insights that aid in the diagnosis, treatment, and overall care of patients. Power spectral density. The PSD is a fundamental concept in signal processing and spectral analysis that provides valuable insights into the characteristics of a signal, particularly in the frequency domain. It quantifies how the power or energy of a signal is distributed across different frequencies. Here, an explanation of PSD and how its analysis can provide insights into signal characteristics. Concept of power spectral density. PSD is a measure of how the power or energy of a signal is distributed across different frequencies. It represents the power content per unit frequency, indicating the strength of or magnitude of each frequency component in signal. Mathematically, the PSD of a continuous time signal xt is defined. S of f is the power spectral density at frequency f, where the S of f is the Fourier transform of st. Mathematically, the PSD of a continuous time signal xt is defined. S of f is the power spectral density at frequency f. Now, x of f is the Fourier transform of xt. The integral represents the power contribution of each frequency component within the signal over a given time interval. In discrete time signals, PSD is computed similar using the discrete Fourier transform and averaging techniques. Insights from the PSD analysis: frequency component identification. PSD analysis allows us to identify the frequency components present in the signal. Peaks and or spikes in the PSD plot indicate dominant frequencies within the signal. This is particularly useful in applications where specific frequencies are of interest, such as identifying heart rate frequencies in an ECG signal. Signal characteristics: PSD analysis reveals important signal characteristics including the distribution of energy or power across frequency components. Key insights include bandwidth. The bandwidth or width of the frequency range containing significant power. Narrow bandwidth indicates a concentrated energy at a specific frequency, while wide bandwidth suggests a broad distribution of energy. Peak frequencies: the frequencies at which the signal exhibits maximum power. In applications like vibrations analysis, peak frequencies can indicate resonant frequencies. Signal dominance: PSD analyzing helps identify whether a signal is dominated by a signal frequencies. For example, a sinusoidal signal or contains multiple frequency components. Signal variability: variations in the PSD over time can indicate changes in signal characteristics. For example, EEG analysis: shifts in power across frequency band can signal transitions between different brain states. For example, wakefulness to sleep. Noise estimation: PSD analysis is valuable for estimating noise characteristics in a signal. By examining regions of low power in the PSD plot, one can estimate the noise floor and assess signal to noise ratios. Signal enhancement: in various applications such as audio processing or communication system, PSD analysis can guide filtering techniques. For instance, you can change or you can design filters to emphasize or attenuate specific frequency components based on PSD information. Diagnosis and monitoring: in biomedical application, changes in the PSD of psychological signals can aid in disease diagnosis and monitoring. For example, analyzing the PSD of an EEG signals can reveal abnormalities associated with neurological disorder. In summary, power spectral density is a powerful tool for characterizing the frequency content and power distribution of signals. It provides critical information about the dominant frequencies, bandwidth and noise characteristics of a signal, making it valuable in various fields including signal processing, engineering, physics and biomedical science. Now, Fourier transform can be used to generate various visual representation of signals in the frequency domain, providing valuable insights into the frequency content and characterizes of the data. The two common types of frequency domain visualization: the amplitude spectrum and spectrogram. Amplitude spectrum: the amplitude spectrum is a straightforward way to visualize the frequency components of a signal. It shows the amplitude of each frequency component present in the signal. A spectrogram: a spectrogram is a time frequency representation that provides a more comprehensive view of how the signal frequency content evolves over time. In a spectrogram, time is represented on x-axis, frequency on the y-axis, and color intensity represents the magnitude of each frequency components at different time points. A spectrogram are highly informative, particularly in applications like speech recognition and audio processing. They reveal how the signal's frequencies changes dynamically over time, making it easier to identify different phenomena in speech or analyze complex audio signals. Spectrograms are widely used in fields such as music analysis, speech processing, and even in the biomedical applications like analyzing EEG signals to study brain activity patterns over time. These visualizations derived from the Fourier transform offer powerful tools for understanding and interpreting the frequency contents of the signals. They are essential for tasks such as music analysis, speech recognition, in many applications where knowing the time frequency characteristics of signal is crucial. The Fourier transform plays a pivotal role in biomedical signal processing for a multiple reasons, show its immense importance in the field of frequency component analysis. Researchers leverage Fourier transform based techniques to gain a deeper understanding of the human body's psychological process and discover new insights into diseases, treatment and interventions. The speed and efficiency of the Fourier transform, especially with fast Fourier transform algorithm, enable real-time monitoring and rapid data analysis critical for continuous patient care. In essence, the Fourier transform is an indispensable tool in biomedical signal processing, serving as the bridges between time domain signals and their frequency domain representation. Its capacity to extract, analyze and interpret frequency information within biomedical signals has revolutionized healthcare by improving diagnostics, enabling personalized medicine and advancing our understanding of human psychology. Without the Fourier transform, many of the critical insights and advancements in biomedical signal processing would not be possible. In conclusion, the Fourier transform plays a vital role in field of biomedical signal analysis and processing. It is a powerful mathematical tool that allows researchers, healthcare professionals and engineers to gain deeper insights into complex biomedical signals by transforming signals from the time domain to the frequency domain. The Fourier transform provides several key benefits. First one, frequency benefits that we have already discussed, that is frequency component identification, noise reduction and quantitative assessment, abnormalities detection, treatment optimization, research and biomarker discovery. So its Fourier transform application extend across a wide range of medical disciplines, making it is indispensable tool for healthcare professionals and researchers alike. Okay, thank you.